In today's pre-lecture, we're going to talk about polynomials with coefficients in different rings. So first of all, we can consider polynomials with coefficients in these familiar fields. So like a polynomial with coefficients in the integers might look something like 5t cubed plus minus 1t squared plus 7t plus 2. A polynomial with coefficients in the rational numbers might look something like 1/2 t squared plus 6t plus 7/3. A polynomial with coefficients in the real numbers could look something like √2t to the 4th plus 5. A polynomial with coefficients in the complex numbers could maybe be 2i times t cubed plus 2 plus I t plus 1. So here we're just taking our coefficients for the polynomial from whatever field we're working with or whatever ring we're working with, and then making a polynomial from that. So we can do this for any ring. So if R is any ring, we can consider polynomials with coefficients in R. So we'd say this R adjoin T, and that's the set of polynomials of any degree with coefficients coming from our ring R. So the T here is telling us the variable in the polynomial. So if we have R adjoin X, for example, would be another way we could construct a polynomial ring, then we just use the variable X instead of T. So the choice of the variable doesn't really matter there. It's really just a placeholder for the variable. Note that we typically only do this when R is a commutative ring with 1, so that means that multiplication is commutative and there is a multiplicative identity. And in particular, we're going to focus on polynomials with coefficients in Z, Q, R, Z mod M for integers M, both prime and not prime, and something that we haven't talked about yet, which is FQ. So this is a finite field with Q elements. This is something that we will define next week. So when working with polynomials, we can, for the purposes of our class, restrict ourselves to coefficients coming from one of these rings or fields. So for now, you can focus on the ones that we've learned so far, Z, Q, R, and Z mod M, and think about coefficients coming from those rings. Once we've created this set of polynomials, we can add and multiply polynomials, regardless of the ring that the coefficients are over. So let's decide that we're going to look at polynomials with coefficients in Z mod 4. So our coefficients are all coming from Z mod 4. Then if we add 2t plus 1, that polynomial to the polynomial 3t squared plus 2t plus 1, well, we'll have 3t squared plus 4t plus 2, but remembering that we're working over Z mod 4, this polynomial is equal to 3t squared, and then 4 is congruent to 0, so this is just plus 2. So one thing you'll notice as we're working with rings in general, we're not going to be using the notation for modular arithmetic as much. We're just going to say, well, we're working inside of Z mod 4. And so then equals would mean the modular arithmetic equals mod 4. If we add these next two polynomials, 3t cubed plus 2t squared plus t plus 3, add that to 3t cubed plus 3t squared plus t plus 1, then we get 6t cubed plus 5t squared plus 2t plus 4, and then 6t cubed, so 6 is congruent to 2 mod 4, so this is 2t cubed. 5 is congruent to 1 mod 4, so this is t squared. And then we've got plus 2t, and 4 is congruent to 0 mod 4, so that's it for that one. All right, we can also multiply polynomials, so this will work similar to how we multiply polynomials over, the real numbers or other things. So we kind of FOIL here, and we get 4t squared plus 2t plus 2t plus 1. So the 4t squared, that's going to be 0. Then we've got 4t, that's also going to be 0. So we're actually just left with 1 here. So you can see that multiplication is doing these things that are maybe not so expected for multiplying polynomials, where in this case we are multiplying two polynomials together and getting 1 from that, which is sort of interesting. And that's something that'll come up as we start to study these polynomials a little bit more. And if we multiply something like 2t plus 1 times t squared plus 3, we get 2t cubed plus 6t plus t squared plus 3. So 2t cubed plus t squared plus 2t plus 3. So this is really similar to normal polynomial addition and multiplication. It's just that when it comes time to add or multiply the coefficients, those operations are coming from our ring R. If R is a commutative ring with 1, then when we look at these polynomials with addition and multiplication, that's also a commutative ring with R. So we talked about this as an example of a ring, that polynomials with coefficients in R were an example of a ring, but we can have coefficients in any commutative ring with 1, and that's going to give us another commutative ring with 1. So one thing to pay attention to here is that if R is not a field, weird things can happen. We already saw that a little bit with two polynomials multiplied together to be 1. If we look over z mod 6, we can see that multiplying 2t plus 4 and 3t squared, we get 6t cubed plus 12t squared. But hey, 6 is congruent to 0 mod 6, and 12 is congruent to 0 mod 6, so this is 0. So we can multiply two polynomials together to get the zero polynomial. So, be careful and pay attention to what's going on in the ring or field that you're taking coefficients from. Sometimes, some surprising things can happen, and we'll be talking about that more as we continue to study polynomials over rings next week. All right, so that's it for this pre-lecture. So answer those questions, and on Friday we'll be talking about the projects as well as reviewing this a little bit.